Okay.
Are you guys have cognition decontraction down? We know it all. If I gave you basically a reproduction of what we did the other day on our first test, that was worth like 30 points, would you be okay? Because I did that, it might have been when Ty took the class in 2 summers ago, and I did that, and like 3/4 of the class, like just completely fucked it up. And lost like 30 points out of like an 80-point test. I'm like, it's super easy. We went over this and we outlined it in class. It was gonna be great. And then everybody bombed. And so I've been very gun shy ever since. But right, you guys are better than Ty's class. Y'all are better than that. Right? We'll see. So we've done it in class twice. We made a worksheet for you. We're gonna keep working on it. We may come back on Friday and actually present some of the information in a slightly different way. Because it's one thing to know it, like memorizing doing the steps, but then the way we learn things is then we jumble up the steps, or we present it in a different way, and you have to think about it a little bit differently, and that helps you remember it better and better and better. So we'll keep doing some of that. And I'll bring some of it up today. Okay. So we're going to quickly do a little bit of road science because it relates to stuff that's going to be here that we're going to talk about today. We're going to continue talking about our ability to generate force. Okay. And so there was, from the list of road science questions, several questions related to genetics and resistance training or genetics, and specifically on development of muscular strength or force production, which is exactly what we're going to keep going over today and Friday. Okay. And the questions centered on, are some of you genetically predisposed to be able to develop more strength than others? Okay. Are you genetically predisposed to develop more strength? And I think for once, the part of the answer to this one is yes. Okay. Genetics absolutely determines muscle mass. Absolutely. Genetics absolutely determines your muscle mass response to resistance training. And we'll talk about that once we get past our first test. There's a whole slew of things that go into that. Okay. But genetics also plays a role in determining most of the things that are on the slide here. Okay. And so outside of muscle mass, we're going to talk a whole bunch today about the idea of motor unit recruitment, the idea of turning on the alpha motor neuron. Your brain signals to the alpha motor neuron, and we get all of that signaling downstream. Okay. Some of you have more alpha motor neurons than others. Some of you have a enhanced ability to control how easy or difficult it is to make those alpha motor neurons polarize. And so because of that, there may be some ability to influence that. All of you are going to have different, as not so much muscle size, but there's other architectural things. We're about to talk about pination a little bit to start with, the stuff we were finishing with the other day. You have different muscle lengths, you have different limb lengths, right? And all of that. And so in that particular way, yes, genetics does play some role in how strong you are right now and how strong you may be able to become when you do resistance. Okay. All of you can get stronger. Some of you are just going to get really strong, and others are just going to get stronger. Okay. Unlike, it's probably not quite as much we know with VO2 max. About 40% of the variance in VO2 max response to training is due to genetics. There are all these really cool stuff on identical twins and things in families. We know that it's very, very powerful that way. The strength response is probably a little bit less, but it does matter. Okay, it does matter. And I'm going to show a thing when we get to training. There are unfortunately some of y'all that will train all you want and you'll never get strong. You're on like the 3 standard deviation tail of the normal distribution. You do all the things perfectly, and you still don't get strong. Okay. There's 80 of y'all in class, maybe like one person, maybe one would fall into there. There's also one of y'all that will get like 400% strong. And we'll get into some of these. So that's kind of what's happening with that. Okay, that's a really good and interesting question. All right, let me see if I can actually make this thing advance. So we finished off the day on Monday talking about muscle size, right? Bigger muscles, more actin and myosin, more cross bridges, more force. Okay, so we're going to get back to that a little bit. We're going to get back to the idea of pennation and how those things come in and attach to a tendon in a minute. But I want to talk about a couple of other things that are going to be important as we go through all of this. Okay, and this is mostly review. You guys have seen this in anatomy. You've probably seen it in principles of health and fitness. If you've taken personal training or anything else, you've seen it there. But it's important, so we're going to cover it again. We classify muscles into these different functional groups. Okay, and so I have a picture up here of apparently what are the elbow flexors. Okay, so you've got the bicep here in blue. Okay, now collectively we call it the bicep, but it's actually multiple muscles. It's the biceps brachii and mostly the brachialis. Okay, those are what we call agonist muscle. An agonist muscle is the muscle that induces the primary movement that you want for anything. Okay, when I do a curl or I do elbow flexion, so I'm flexing up, those are the two primary muscles that are doing that. Okay, they have origins up here at the shoulder. They have insertions down here on, I don't remember, somebody can tell me if this is the radius or the ulna, one of the forearm bones. It doesn't really matter that much. Okay, down here, we then have a thing called the brachioradialis that runs across like so. That's what we call a synergist muscle. It's not the muscle primarily responsible for movement, but when it contracts, it pulls a little bit. It gives us a little extra nudge in a certain direction. We then also have the antagonist muscle or the tricep. This is the muscle that's responsible for elbow extension. Okay, for elbow extension. I need to illustrate using all of this concept for you guys that I hope will make everything else that we're doing make a little bit more sense. Okay, it's going to make a little bit more sense. So what I want everybody to do is stand up and grab your backpack if you've got a backpack. If you don't have a backpack, just grab something to hold on to. Okay. All right, I'll do it with mine too. So do this with me, okay? Take your backpack or whatever you've got and put it down like so. Okay? Now, curl it up with me. Up, up, up. Okay? Down. All right. Now, relax for a second. Okay? We're going to ask, just going to pick somebody who can I see in the midst of all of this. Justin, you're right here. Sorry, buddy. Okay, Justin, how much does your backpack weigh?
Maybe 20 pounds.
Maybe 20 pounds. Okay, you got too many books. I'm sorry, I'm probably contributing to that. Okay, you think it weighs 20 pounds. If you want to curl, all of you have some bag or something, it weighs some amount. Why does it weigh 20 pounds?
Oh, a water bottle. I have books in it.
No, right, but why do your books and your water bottle collectively weigh 20 pounds? Why does anything weigh anything? Gravity, good, okay? Gravity is pulling it down, okay? Pulling it down. So if you want to pick it up, how much force must you generate using your agonist and synergist muscles in order to pick it up? More than 20 pounds, good. When you want to lower it down, how much force must you generate? Less than 20 pounds, right? I don't know what I have in here, right? But I can do no force, right? Just let it fall, okay? How much more than 20 pounds do you need to generate? How much more than whatever your bag weighs? Let's do this again. Slowly. Slowly, slowly, slowly. Good. How much more force than whatever your bag weighs must you generate to get it to move? Is it a little bit more? Is it a shit ton more? Like how much? Right? A little bit more. What happens if you generate way too much force? Right? Okay, we do that. All right, you guys can sit down. Thank you all for participating and coming to my TED Talk. Look, I do this because this is amazingly important. Okay, your bag weighs a certain amount. Okay, it weighs a certain amount. You need to be able to generate just enough force to overcome gravity. No more, just a tiny fraction more. Okay, in order to make it move. If you generate way more than you need, right, then you don't pick it up in a smooth manner. You don't pick it up slowly. You throw it back over your head or something. Okay. The consequence of force production to induce movement is very simple. Okay. We generate just enough force, just enough to overcome gravity, just enough to move at the speed, okay, through the range of motion that we want, no more. If we are inefficient in that way, we are uncoordinated. Okay, and I apologize, I'm losing my voice, bro. It was better today than it was. Okay, but you become uncoordinated, and when we generate more force than we need, we waste energy. We waste energy. It's metabolically inefficient. And so the job of all of the things that we're doing are to use just enough muscle, right? Which means we turn on just enough motor units to induce a contraction through the range of motion that we want, using just the right agonist and synergist muscles to get whatever force we need to generate that movement. Okay? Now, there's one other piece that I'm going to talk about really quickly that you guys also have to appreciate. Okay? So I would tell my daughter, I didn't lie to her, I just forgot to tell her something. Right? She's very black and white on these kinds of things. Okay? Which is great because she's 6, and that's good. It never occurs to her to like actually not tell the full story. But I told you guys that you have to overcome gravity to pick the thing up, which is true. But that's not the only thing you have to overcome. As you pick something up, or if I'm doing squats, as I squat down, okay, the antagonist muscle is never completely silent. It's never completely turned off. Okay. So you're always in that curl getting a little bit of force from your triceps. So that's not great, right? The tricep is trying to extend my elbow rather than flex. So I have whatever the mass basically of the thing I'm trying to pick up. Okay. I have to generate enough force to move that mass and overcome gravity, but I also have to generate enough force to then further overcome the counteracting force of the antagonist muscle. Okay. So anytime we are doing a movement, you're usually getting from a little bit to a lot, and we call this a co-contraction. A co-contraction of the antagonist muscle. So when you pick up a 20-pound dumbbell, it weighs 20 pounds because that's what its mass is by gravity. And you have to generate 20.00001 pounds of force, right? If your tricep was completely silent, but it's not. And so maybe you're getting a pound or something of force from your tricep. So you have to generate 21.00001 pounds of force to pick that up. Does that make sense? If we understand that, then doing a concentric and an eccentric and an isometric contraction will make way more sense. And how and why we control the nervous system, and we turn on motor units one at a time, and we modulate force in very small units, makes way more sense. Okay? Because the outcome is due to the physics of all of that. Okay? We'll do some more examples as we go. You guys with me so far? Okay, sweet. So, you've seen these things already. Okay, you've seen these things. Talk about the type of muscles, let's talk about the type of contraction or muscle action, okay? When I take it up, that's a concentric contraction. When I hold it steady, that's an isometric contraction. When I lower it down, that's an eccentric contraction. That's heard and you know about all of those, okay? There's some fun things that go on because of the structures and how we do these contractions, okay? When I do a concentric contraction, okay, I can generate the least amount of force of all contractions concentric. Okay. The least amount of force. Whatever you can pick up, okay, you can hold or lower down more. Okay. Concentrics generate the least amount of force and they cost us the most energy. Why do they cost us the most energy? Think back on the cross bridge cycle. We're going to tie these things together. Where are we actually using ATP in the cross bridge cycle? What was that, Kate? When it relaxes, right? I have to use energy to break the cross bridge, to turn off the force, and then it can go back to its high energy state, and it can bind again, and I can get another bit of force. So as I do up, I'm getting tens and hundreds of thousands of cross bridge cycles that are going attached, power stroke, break, attached, power stroke, break, as I'm coming up. So it uses energy. The fact that as I use the energy, the cross bridge breaks means that at any instant in time, not all of my cross bridges are actually engaged. So I get a little bit less. A little bit less. Isometrically, I'm just holding it, okay? It's either I hold it steady or I'm not strong enough to move some sort of big heavy object like this desk. When I push, okay, nope, I'm very strong today. The desk does not have a lot of friction, but you push on something like a wall and it won't go. Muscles don't change length. Okay? Because they're not changing length, we are not actually going through the full cross bridge cycle. You engage, you start to get a power stroke. Whatever you're going against, right, is too heavy. You can't win. Gravity is winning, or at least you're equal. So we're not breaking cross bridges. So you get a little bit more force maximally, and it doesn't cost us too much energy. So it costs more energy to pick the bag up than it does to hold the bag. Okay. Any of you that have ever had to hold a 53-pound 6-year-old would be well aware of that. Once you get them up, it's okay. You can hold them and stand there, that's fine. But holding them and down and up and down, or holding them and walking up the stairs or things when they're sick and all of that, more energy, concentric contractions. Okay? Eccentric, on the other hand, when you do an eccentric contraction, you let gravity win, right? I am here, I generate a little bit less force than what gravity has, and I let gravity win and I slowly lower it down, or I just turn off completely and I let it fall. Eccentric contraction, the muscle is getting stretched out, okay? During eccentric contraction, you form a cross bridge and it just holds on, it does not have to break. Okay? It does not have to break. And so you can get way more force. You can lower down way more than you can ever pick up because you can engage the cross bridges. They make their force, and then you get extra. Anybody guess know how rubber bands work, right? You pull a rubber band out, you have all of that connective tissue, the endomysium, paramysium, the epimysium, plus your tendons and your ligaments. They're like rubber bands. And so as you pull a rubber band out, right, and it stretches, it has elastic energy in it. And it's resisting against you trying to stretch it out. Okay? And then when you let it go, it wants to fly back into its original position. So when you do an eccentric contraction, you have resistance against gravity from the connective tissue in your muscle. And so it lets you generate a little bit more force. You don't have to generate as much force in a submaximal contraction, right? If I'm lowering 20 pounds, I need to generate like 19.999999. I'm going to get a couple pounds of that force from the stretchiness in my connective tissue, so my muscle only has to generate like 17. So what that means then is that I've got extra, so I can actually lower down not 20, but I can lower down 25 or something. Okay. Also, because the cross bridges don't break, it doesn't cost us hardly any energy. All of you do this every day, and you don't even realize it. You know it intuitively that these such contractions don't cost us energy. Anybody live like on the second floor or the third floor of a dorm or your apartment or something? Okay. It's real easy to come down the stairs. It's way easier to go down than to go up. When you go down, you're doing eccentric contraction with your quads and your glutes. And the reason it's easy to go down is because those are primarily eccentric contractions. They don't cost you as much energy, and it's easier. We have a larger capacity to generate force when we go down. You weigh the same. You're covering the same vertical and horizontal distance, right? But up is a concentric contraction. It costs us way more energy than down does. And so it's because of the nature of these contractions why running uphill is way more energetically costly and feels worse than jogging and running downhill. Okay. And again, it all comes back to how cross bridges work. And it all comes back to the signals we send from the brain to activate and initiate this cross bridge. So when I tell you that we have to understand how actin and myosin bind together, how we get to that particular place, the state of ATP in the cross bridge cycle, it's not because I want you to have to memorize some terrible shit. It's because this is why. This explains why it's easy to go downhill and it's harder to go uphill. This explains why, right? It's much easier. I guess it's Wednesday. We're not quite ready for second chest day, but why it's easier when you're going to squat to go down. You can take a whole lot more weight down than you could ever hope to go up, right? When you do a squat, you never fail from here. You're like, and fall down. No, you fail when you're way down here because you can't start back up. You can do the eccentric, you can't do the concentric. Where you can do the isometric and hold it, but you can't do the concentric. Okay? And it all comes back to how the cross bridges work. And it all comes back for upstream of that for how the brain can tell the alpha motor neurons to turn on to get us those cross bridges. That is how and why we put force into movement and into motion. Okay. And that's why I make you guys memorize all of those steps. Because it's unbelievably important. Okay. So you guys kind of get that framework. And we spent a lot of time here. But I think it's really important to conceptually understand what all is happening. Okay. Because one of the things that we're going to do is we're going to say, look, big muscles, more force. Great. You get that. More cross bridge. Better motor unit recruitment. You turn on more of those motor units, you get more cross bridges, more force. That's conceptually easy. But then there's more complicated things like the speed of contraction matters. When you go slow, you get more force. When you go fast, you get less force. And it's because of the way the concentric contractions work. It's because of the way the cross bridges have to cycle to do all of that. And we'll get into that. But again, it's really, really important that we understand those underlying anatomical kind of things. Okay. Have I confused you? Think we're doing okay? Okay. All right, we'll see. We'll see. If not, we'll just squat and we'll do an isometric squat and make you guys tell me what's happening and all of that. Okay. So here's one of my favorite graphs. What I will try to do as we go through class at times is I will try to show you old research studies that proves probably a word that gets me in trouble, right? I've done my own research, and this is the things that show up in the text. Okay, what you see here is data that were published in 1952, and we have two bicycles they're sharing a chain. So one person rides in one direction, and the other person tries to ride in the other direction. Or one person rides forward, and then the person on the other bike provides some resistance against them going forward by going backwards. Riding the bike is a concentric motion, okay? It's concentric. Resisting going backwards on a bike is an eccentric motion. And so what they did was they had people ride on both sides. They measured the oxygen consumption of the person going forwards and the person going backwards. Concentric contraction going forward, eccentric contraction going backwards. It's the same work, right? It's the same amount of work, right? Here's this kilogram meters per minute. You guys remember kilopounds from those stupid broke ass Monarch bikes we have over in Collins? And you guys had to do that lab in health and fitness, right? So basically, this is 0.5 kp. This is 1 kp on those things. That's how that works. When you go forward, it costs us way more energy. VO2 is way higher. Okay. When you go backwards, very, very little. Same force, almost no, right? Like, 2/3 less energy expenditure going backwards. This is the biking equivalent of going up the stairs and coming down the stairs. Okay. This is from 1952. I didn't show it here, but they also did a really fun thing on all of this that I used to do in class. And then I decided against it because I felt like people got embarrassed, but they put a big, strong guy on one bike trying to go forward and a much smaller woman on the one going backwards. And they're like, basically have a tug of war on the bike and see who wins. And the girl, because she gets to go backwards and do eccentric contractions, kicks his ass all the time. Okay, and it could be the same thing. We could do it the opposite way. We could have a big strong woman on one side and a very small gentleman on the other. It doesn't matter. We can overcome, right, differences in maximal strength by just changing the kinds of contractions that you do. You can get way more force theoretically doing eccentric contractions. Okay, and this is a thing that we just accept as fact now. But in 1952, here's the first evidence sort of proving what's actually going on. And so I really love experiments and things that are kind of like this. Okay. So this is the stuff we talked about on Monday. We talked about that muscles come in different shapes and sizes, right? My quad is short and thick and enters at an angle. My hamstrings are long and slender, okay? All of your different muscles have different shapes and different sort of anatomical structure, and it's very much related to the job that those muscles need to do. Okay, your muscles look the way they do because of sort of your shoulder muscles, your delts, and your rotator cuff things, because of how we want to move at the shoulder. Right, your quads look the way that they do because of what we need to do from a propulsion standpoint for upright walking. If you look at the anatomy of, say, four-legged animals, it looks a little bit different. Okay, it looks a little bit different because bipedal walking versus quadrupedal walking or running is slightly different. Biomechanics are different. And so we are all going to look a certain way because of that. Again, though, some of you genetically have better shapes to allow for sprinting or jumping or distance running or something like that. Okay. All right, we talk about length. The longer a muscle is, the faster it can contract. Hamstrings are long so that we can reach out and we can quickly pull backwards, okay, and do knee flexion. Larger cross section, right, larger out, as I drew on the board the other day, larger cross section, more force, okay. So muscles that have a large cross section are designed for force. Those that tend to be smaller and longer are designed for velocity, okay. These pieces of steak that you see here are actually MRI images from my dissertation of my leg. Okay, I would be terrified to see what it looks like now. But this is my left leg. You're looking up through my heel, hamstrings down here. That is the black part. The really dark part is
That's my femur. The really bright part in the middle of it is the bone marrow, and then the stuff around the outside, that looks like prime rib is subcutaneous fat. Okay, and so in general, big, as it gets bigger, as the cross section gets bigger, more force. There's other things we have to sort of lay over the top of all of that, but in general, larger muscles, more force. Okay, we left off on Monday talking about the direction at which the muscle fibers, right, in the muscle are oriented relative to the tendon of that muscle that we pull onto and move. That idea is called pennation, okay, pennation. So imagine here's my patella tendon, okay, my tibia is up here, my femur is here, the knee joint is right here. All of my quad muscles are going to connect to that patella tendon at an angle like this, okay? They're going to come in at an angle. If it's a hamstring, the tendon is like this, then the fibers are going to pull directly in line with the tendon. So the pennation of my hamstring is basically 0. And in your quad, you have a pennation that's, if you measure this small angle here, this may be 20 to 25 degrees. Okay, and I'll explain why that's important in a minute. You don't have to memorize all of these different kinds of things, but it just illustrates, right? On the left is what we call a fusiform muscle that has basically no pennation. The fibers all run parallel to the tendon. The sartorius, your hamstrings look like this. Okay, I say that, and then of course the next one is the semimembranous, which is one of the hamstrings. But there's a tendon, and they all come in from one side. Most of your quad muscles tend to be what we call bipinnate. It's in the middle, and they come in from both sides, kind of like a leaf. And then don't even talk about your deltoid and your pecs and those things. You got stuff coming in like a hot mess from all over the place. Okay, but the idea behind this is there's a reason that certain muscles are fusiform and certain muscles might have a larger portion of pennation. Okay, but to understand this, we need to do an experiment. Okay. Okay. Usually I do this by having you guys push each other. But we'll see how this goes. Okay. I am, let's just say, okay, I'm a hamstring muscle, and I'm going to grab the tendon and I'm going to pull on the tendon, and I pull it like this, right? So all of the force that I'm generating with no pennation is pulling the chair in the direction that I want to go. Okay. Pretty easy, pretty straightforward. Every bit of force in the fusiform muscle gets transmitted onto the tendon. I'm a quad muscle, okay? And I'm coming in at an angle. I'm going to try to pull this chair at an angle. But remember, some of you may be like me and may have a patella tendon that doesn't track super well on some of this, okay? I want the chair to move forwards and backwards, but I can only pull on it from this angle. Okay, so when I pull from this angle, right, it has a forwards and backwards component, and it also has a side to side component. Okay, not all of the force that I apply to the tendon is applied in the forwards and backwards dimension. Okay, does that make sense? Right, if you push your friend right from behind, they go forward, or you pull them from there, but if you're on the side, they kind of go at an angle. And the degree of that angle is related to how much forwards and backwards versus how much side to side, right? You're somewhere, if I'm at like 45 degrees, those are kind of even themselves out. So what that means is when I have pennation, I lose force. I lose force as it gets applied to the tendon for the direction that I want to go. You may think, well, Dr. Black, that seems stupid. Why would we ever be set up in that way? To lose force? Well, what happens is I only have so much space in my muscle. I only have so much space wherever we are, right? And so if I've only got a certain amount of space, I can't get super wide, let's just say, in these fusiform muscles. I can't get out really, really big to have a lot of force. But if I come over here, let's just say, I can be entered here, 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 I can come all the way up like this, and and I can be bipinnate, and I can also get all the way around over on this side. And so having pinnation lets us pack in more fibers than being fusiform does. And so it's a trade-off. More fibers, more actin-myosin, more cross bridges at the expense of losing some of the application of that force. But at the end, we end up in a place where we win, we get more force overall. Okay? Whereas fusiform, the muscle's not as big, and we're getting all of that force. We're very efficient at transmitting that. Okay? Does that make sense? We can measure this pennation angle. Come to the lab, we'll take an ultrasound machine, and just stick it on your leg, and we can see those fibers, what the angle is. All of you have a different pennation angle in your quad and in all of your different muscles. Okay? Some of you in your quad have a more narrow pennation angle, which means a larger percentage of the force you generate in those muscles gets transmitted to the tendon. It's good. That might be a reason why somebody's a little stronger than somebody else. They have a little narrower pennation angle. Okay? And so this is an idea of how these things are going to be applied with muscle architecture. Okay? So we call this idea of accounting for pennation something called physiological cross-sectional area. Don't worry about it. I'm just showing you. This is sort of a graduate level kind of thing. But the idea is basically you have a hamstring, let's just say on the left, and your cross-section right is that line that you can see right there. Here on the far right, you've got one of your quad muscles that's going to come in at an angle from both sides. But the actual functional cross-section is this whole sort of half circle or half oval that goes all the way around. So you can see by coming in at an angle, I can get a way bigger physiological cross-section. Okay. I lose some force because of the angle, but I compensate for it with that. So most of the muscles are large muscles in the body that generate lots of force. They have pretty consistently sort of these large physiological cross-sectional areas because they are more pinnate than our smaller muscles. Okay. All right. How many of you do short? No, yeah, we'll do this way. How many of you know someone who is roughly your size, or maybe smaller than you from a muscle mass, and yet they are stronger than you? If you went to the gym with them, right, they can squat more than you, they can curl more than you, they can bench more than you, whatever you're doing, they can do more than you, but they're roughly equal to you in size and muscle mass, or they're small. Anybody know? Anybody know those people? Yeah? Okay. You all do know what the gym is. You've been to the gym, right? That kind of thing. Okay. Like I'm losing y'all a little bit here. Okay. Right. Okay. How is that person stronger? How? You're like, man, I got bigger muscles than you. How can you lift more than me? Right? Do you even work out, bro? Okay. And the primary reason that person is probably stronger than you comes down to this idea of what we call motor unit recruitment or motor unit activation. Okay. You have a certain amount of muscle in your body. Some of you are like me, and I have muscle, but I can't use all of it. My brain has forgotten how to activate all of the muscle that I have. If I go to do a squat, okay, you tell me, Coach Black, squat as much as you can. I cannot turn on and engage all of the muscles in my quads and my glutes to be able to squat today. Okay? I have forgotten how to do that. Mostly because I haven't done a squat in, it's not been 30 years, but it's pretty fucking close. Okay? I assure you I have not done a power clean since I left high school. My dad, the football coach, was like, "Did your back hurt? Power clean." Right? Having a hard time seeing, power clean. Whatever it was, power clean would fix it. Okay? So I have immaculate power clean form. Immaculate form. And it's the worst thing in the entire world. Okay? So after high school, it's like no more squats. I'll leg press, but I'm not gonna squat. I could then. I don't know, I weigh more now than I did then. I had more muscle then, but I could, because I was trained, turn on a higher percentage of those motor units. Okay? So your friend that has less muscle than you, that is stronger than you, the most likely explanation is maybe they can recruit 95% of the motor units that go to their quads, and you can only recruit 85%. Okay? And if you're roughly equal in muscle mass, their ability to use and engage more of it means they're stronger. Okay? That's how this functionally works. It's the most logical explanation for most people that are of different sizes. You know, there could be things about lever arms and some physics and stuff that we'll get into on Friday, but most of it is motor unit recruitment. Okay? When I say recruit, I mean to polarize the motor neuron. The brain sends the signal down the spinal cord and it polarizes the motor neuron, and we get all those downstream effects, down the axon, across the junction, down the T-tubule, into the SR, release the calcium, get the crossbreak. Okay? If you're better at doing this, you can recruit a larger percentage of what you have, you're likely to be stronger. Okay? If I made every one of you pick your neighbor up and put them on across your shoulders, be a fun TikTok video. We'll get some, we had a class, we'll get some views on that one, right? Pick your neighbor up, hold them across your shoulder, and squat today until you can't squat them anymore. And then we come back on Friday and we do it again. Almost every one of you would be able to do another rep on Friday than you could today, because you're better at this. Your brain learns and remembers and gets better at doing this. Work out today, stronger tomorrow. You don't have more muscle. It takes months to get more muscle, to get more crossbreaks. Months. Stronger tomorrow because you're better at recruiting your motor units. That pathway from the brain to the motor neuron comes in hands for a whole bunch of reasons that it comes in hands. Right? So if muscle mass is the most important thing, right? Big person, very likely going to have capacity most of the time to be stronger than a very small person. In people that are roughly the same size or pretty close, it's your ability to recruit whatever motor units you have. That's the primary differentiator. That's the primary differentiator. When you turn them on, you turn on the smallest motor unit. So the motor neuron connects to the fewest number of fibers. Those fibers tend to be slow twitch. That goes first. Because remember, when I pick up the bag, I only need to generate just a tiny fraction more force than gravity and my tricep are generating to get it to go up. Okay? So when I do this, I go 1 motor unit, not enough, no movement. 2, no movement. 3, 4, 5, 6, 7, 8, 9, 10. Okay, 25, it's starting to move. We get, we're in this point, we're at the sticking point. Give me a 26. Okay, good, I got it. Up. Only the bare minimum number of motor units recruited to initiate that movement. Okay, and so our ability to run quickly up and through that gives us very, very fine control of force production. You don't get extra force, you get only the amount that you need. You're not wasting cross bridges, you're not wasting force, you're not wasting energy. You ever do something and it's brand new to you? And you feel really uncoordinated doing it? If I asked all of you that have never swung a golf club to come down and try to swing a golf club, right? You're not gonna look like Tiger Woods on the first swing. Right? Because you do not know yet the right way to do the motor unit recruitment. You're guessing, right? But you haven't practiced it. So you get weird force production and you're not controlling it in the most precise manner. But you learn. Do it today, better tomorrow. Do it tomorrow, better the next day, and the next day. And eventually we sort of burn in that motor path. Okay. So we illustrate it like this. Okay. I know you guys have seen this, but let's illustrate what I was just showing you. Okay. What I'm showing, this is called the Henneman size principle of motor unit recruitment. you recruit the smallest motor neurons that have the smallest soma or cell body to their neurons in your spinal cord first. So you can see here on this graph, the number of active motor units, which ones are recruited, which is how much force we get. Here's a whole muscle. I need a tiny amount of force. You're going to curl up your pencil. Okay. 1 motor unit. Note, this is really important. The fibers that are connected to that neuron are distributed all across the muscle. They're not all clumped together in one place. This is really important. So when you generate a low amount of force, you're not just like activating the top part of your brachialis. They're spread evenly everywhere. It helps us have better force transduction. Okay. Okay. I need to pick up 2 pencils. So not 1 motor unit. Now I get 2. Okay. Now I get 2. Okay. Now we're going to add your, I don't know, your giant water cup on top of all of this, right? All of you with a Stanley. My daughter came home this summer and said, Daddy, I need a Stanley water cup. And I was like, you're 5. Like, calm down. My wife was like, I don't have a Stanley. We gave her a fake one. And she was like, no, it needs to be a Stanley. I'm like, you won't even drink the water. I don't care. Somebody at daycare had one. So kids, man, kids, right? You pick up your Stanley. Now you got 3 motor units. Okay. They're getting larger and larger. They're all still type 1 as we move our way up. Ping, 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 ping. Okay. Eventually, you run out of type 1 fibers. You run out of type 1 motor units. And so then you turn on, and I know that I did this wrong, and it's been pointed out to me, and I apologize, but you'll see these larger blue ones. These are 2A fibers. I know that there's not more of those than there are of the smaller, that last type 1 one. That was an oversight on my part. I made this in PowerPoint. It took me hours. So I'm sorry. But you eventually get type 2 fibers now. Okay? You get type 2 fibers. More force, but now I'm starting to use more energy. I need more force still. Some more type 2 fibers. Eventually you run out of 2As and you get to, now I'm going to get 2Xs. I'm going to get those very, very big ones. I think that's all. Yep, that was it. Okay. And you get those. Okay. Most of us are not very good in movements we're not used to doing at recruiting the 2X motor units. Those last 3 or 4 or 10 or 100, depending on how big the muscle is, those 2X motor units, because we don't use them very often. Okay, we don't use them very often. And that's what's going to give us this capacity to be able to increase our strength. Okay. Does that make sense? Okay. We're going to stop here. We will pick up on Friday and we'll add velocity and range of motion and things. I'll get through all of this for Friday. The take-home worksheet assignment is due on Friday, right? Ty is going to have office hours on Thursday in our lab over in Sarkins from 11 to 1. If you'd like to come and see him, we're probably going to have a test. Right? A week on Monday. Okay? Are you guys filling out the study, the like lecture notes and the study thing? The questions? Bye guys, see ya. I love when they look at me like, what?
Yeah.